Chapter 8, which looks at developing meanings for the operations, is all about helping children connect different meanings, interpretations, and relationships to the four operations of addition, subtraction, multiplication, and division so they can accurately and fluently apply these operations in real world settings. This is all part of the operations core, in which students learn to see mathematical situations in their day to day lives or in story problems, and they begin to make models of these situations. This whole chapter is about helping students develop operation sense.
One way to really ignite student interest in mathematics is to use contextual problems that model real-world scenarios, or even using them within the problem. If you do so, that makes the problem relatable, and it will help to activate their problem-solving strategies. The context that you're going to put these problems in, again, are going to be something that is familiar to the students. And the important thing for you is to make sure that the students, through their problem-solving strategies, are using numbers, words, or pictures that make sense, that their problem-solving process can be expressed in a way that's logical. Within the next two slides, we're going to look at three categories of problem structures for additive situations. These three structures are called change problems, part-whole problems, and compare problems. I want to encourage you to explicitly teach your students these structures so they can identify important characteristics of the situations and determine when to add and when to subtract. With respect to change problems, there's two types, join problems and separate problems, and they're illustrated by the graphics that are on your slide with A and B. Here's an example of a join problem. Molly has 8 pennies and Mike gave her more. She now has 12. How many did Mike give her? This could be modeled by joining 8 to something unknown and being set equal to 12. How about a separate? Well, let's say Molly had 12 pennies to start with, but she gave some to Mike. She now has 8. How many did she give to Mike? So we need to separate the whole and a part and find the leftover. That would be modeled by 12 minus something unknown equals 8. So those are two types of change problems. And notice, for both of those, they deal with the same exact units. What about a part-whole? Part-whole problems are also known as put together or take away problems. They're different from change problems because there is no action of physically joining or separating the two amounts, and they don't have to necessarily be the same units. In these situations, the whole might be unknown, one of the parts, or both of the parts might be unknown as well. An example would be this. Let's say Claire has 4 pennies and 8 nickels. How many coins total does she have? Or Claire has 12 coins total. Some are nickels and some are dimes. How many of each could she possibly have? And you see the graphic of the part-whole demonstrated on the bottom of your screen in the right-hand corner. The last type of structure are compare problems. Compare problems involve the comparison of two quantities. The third amount in these problems does not actually exist, but it's the difference between the two amounts. Like part-whole problems, compare problems typically do not involve a physical action. Comparison problems generally use the words how many more or how many fewer. For instance, the problem, John has 4 fewer pennies than Sam. Sam has 12 pennies. How many pennies does John have? That represents a compare problem. I do want to make a note of something that deals with mathematical terminology at this point, and it's the difference between semantic and computational equations. A semantic equation has an unidentified part plus a known part equal to a whole. A computational problem has the two known parts on one side equaling the unknown. And in math, we've often been taught to always put an equation into computational form because we're looking to find what the answer is equal to. But it's really important that you Start to show your students from early on that both forms are equivalent, because the somatic form is the one that usually students will initially write a problem out in because it mirrors the order of the words. So again, if you can take opportunities to show them, like the problem on the screen, that blank plus 5 equals 11 really mirrors the same exact concept as 11 minus 5 equals blank. Okay, I'd like you to take some time and read through A, B, C, and D on the slide here, and then try to identify the structure that each problem represents. To check your understanding, you could look in the notes section of the slide. I identify which each structure is. This screen presents a contextual problem and a student's explanation of how he solved it. You'll notice in the problem that real students' names were used, and that's so helpful within your classroom to make the problem relevant and relatable to the students by using their names. It ignites their interest and really gets active learning happening in the classroom. Some different ways you can derive some contextual problems is by using recent experiences in your classroom, whether that be through field trips, children's literature, art, science discussions. All of those are fruitful ways that could yield great contextual problems. A couple of things I do want to mention before moving on. One thing that really differentiates contextual problems from solving story problems is that not only are they relevant to the students in your classroom, but you really want to emphasize the need for students to explain or put into context what they did within the scenario that you've presented. And it needs to be done so well enough so that someone else can understand it. This is a huge vital part to developing mathematical literacy and computational fluency on behalf of your students. Having students share and perhaps grade each other's work is one way to achieve this end. It's important, too, that when we are designing contextual problems, that you choose numbers that are appropriate to the Common Core state standards. So, for instance, you'll want to use numbers between 0 and 10 for kindergarten, up to 20 for first graders, and so on. So check your state standards to make sure you're using appropriate numbers. In addition, you want to begin introducing the minus and plus signs in kindergarten and continuing to do so in first grade as a way to record thinking. The equal sign should also be introduced, and you want to make sure that you define it as meaning is the same as. I think sometimes students associate equal with meaning the answer, but they're going to often be using equal signs just to show that one expression is totally equal or equivalent is the same as a whole nother expression. So if we can start out by just phrasing it as is the same as, that will help students make that connection early on. Let's continue talking about teaching addition and subtraction. Many of your students will want to use counters, bar diagrams, or number lines to solve story or contextual problems. The figure on this slide to the right shows some different part whole models for 5 plus 3 equals 8 and 8 minus 3 equals 5. Notice that in every example, both of the parts are distinct, even after the parts are combined. Let's talk about the number line, which is pictured in the lower right corner. A number line is an essential model, but it actually can initially present some conceptual difficulty for students below second grade. This is probably partially due to the students' difficulty in seeing the unit. And this could be a challenge because it appears on a continuous line. But it's very important that students become familiar with number lines early on, because they really begin to use them heavily in third grade when introduced to fractions. And it's important when you're introducing students to the number line that you really focus on the space between the tick marks. That space or length is the unit. And if students just look at the tick marks, they can totally miscount or misjudge the number line, but you want them to be thinking of the number line as measuring a length unit, and each length unit is equal to 1 unit. Using arrows or hops like you see in the lower right-hand corner of the number line can help to illustrate the length concept as we see with 5 plus 3 equals 8.
I want you to take some time and read about activities 8.2 and 8.3 on page 163 of your text. In fact, hit pause on the PowerPoint right now and come back in a few minutes. Okay, now that you've read the activities, let's talk about something. Note that in both activities, you end up with two distinct parts, even when there is a remove action. The remove part remains on the mat as a model for an addition equation to be written after writing the subtraction equation. A discussion of how two equations can be written for the same situation is an important opportunity for you to take in order to connect the operations of addition and subtraction. Thinking about subtraction as think addition rather than take away is significant for mastering subtraction facts. Because the tiles for the remaining part or unknown add-in are left hidden as they are in B on this slide, a student doing this activity is encouraged to think, what goes with the part I see to make it the whole? Let's talk about some important properties of addition and subtraction, namely the commutative and associative property. While the commutative property may seem blatant to us, it's not necessarily so for children. While you should definitely use the precise title of the property when introducing it to your students, know that you really care about a student's understanding of the property itself. Reversing the order of two sets of counters can help students visualize this property. Talking about when the property works with recognizable numbers and perhaps really large ones will help to make it more understandable for students. The associative property is critical because it helps students add efficiently by looking for add-ins that will produce 10, like the written work shown on this slide. Activity 8.4 on page 165 of your text is an excellent activity for helping your students become fluent with the associative property and their natural instinct to hone in on anchors of 10.
Okay, we're going to move on to multiplication and division problems. Most researchers identify 4 different classes of multiplicative structures: equal groups, comparison, area, and combinations. The first 2 are most prevalent in elementary schools, equal groups and comparison, and the latter 2, area and combinations, are used in 3rd grade and beyond. It is important to know that these structures are used not only for multiplication but also for division because they're inverse operations. Within the equal group problem, which is usually the first way that multiplication is introduced, you have one number, which we call factor, and it usually stands for, represents how many groups are involved. The second number or factor tells the size of each of these groups. And the third one, which is your product, tells the total within all of the groups. I want to show you a couple examples of problems that fit within the equal group structure. Let's say you pose this problem to your students. If apples cost 10 cents each, how much did Jill pay for 5 apples? You have one type of item that's costing an equal amount. You could also pose an equal group problem through division. Let's say you said Jill bought apples at 10 cents each. She spent 50 cents total. How many apples did she buy? So this is a way for students to quickly recognize this is an equal group problem, this is multiplication, I'm either going to multiply or divide depending on the structure of the problem to find the solution. Another type of common multiplicative structure is the comparison problem. And it's not so much important that students are able to name what type of multiplication structure a problem represents, but rather they realize that it's a multiplication problem, period. And so the more examples that you can provide your students, the more they're going to be able to hone in on, okay, I'm going to use multiplication or division to solve this problem. With comparison problems, you're not necessarily looking at equal groups in a blatant way. Instead, the problem presents 2 groups whose size are being compared, for instance, and one is a multiple of the other. So the phrasing is different. And within these problems, there are 3 possibilities for the unknown. One could be the product, and here's an example of how an unknown product would be phrased. Let's say you were told Jill picked 5 apples. Mark picked 3 times as many as her. How many did Mark pick? 3 times 5 would be 15, so that's an unknown product. It could be the actual group size, and here would be an instance of a problem with an unknown group size. Mark picked 15 apples. He picked 3 times as many as Jill. How many did Jill pick? So we realize that we're using division here, and again, it's a comparison between two quantities. So we'd have 15 divided by 3 is 5. Lastly, it could be number of groups that is unknown, and here would be a problem that is phrased with an unknown number of groups. Mark picked 15 apples. Jill only picked 5. How many times as many apples did Mark pick? And students would know division is the key, and they would do 15 divided by 5 to receive an answer of 3. The last two multiplicative structures are area and array problems. Area problems are totally different than the prior two because the product has different units in the two factors. So if you had a little garden plot that measured 4 feet by 7 feet, equaling 28 square feet total, you realize that your total units, square feet, are different than the singular feet that you had for length and width. An array is actually a visual representation of the equal group situation that we talked about first. So why isn't it placed with equal groups? Well, visually, it's a great lead-in to area, so the Common Core State Standards groups it with your area problems.
When teaching multiplication and division, it is essential that you use interesting contextual problems instead of more sterile story problems. There's a great problem on page 169 of your text that talks about the students measuring how many yards of paper it takes to cover a bulletin board and then counting how many more of that same size appear throughout the school and then having to determine from that how much paper they will need total. That's something that's kinesthetic and relevant to the students' lives. So it's something that they could then do and then come up with meaningful results. It's essential that we use these interesting contextual problems. In addition, for division, it's really important that you do not use the phrase goes into, but instead say something like how many groups of such and such are in such and such, like how many groups of 6 are in 24. We tend to use the phrase goes into too often, and it doesn't help students really conceptualize what division is implying. Another thing that's very important is that you help students understand what a remainder truly is. We don't want to just talk of them as like R3 or leftover. For instance, when you have a student divide 11 by 4, that equals 2 3/4, not 2 remainder 3, but you want them to realize that that really means there's 2 full groups when you take 4 and divide it into 11 that are formed, and there is 3/4 of another group that is full. There's 1/4 of it that's not full, but 3/4 of it that are then filled. But remainders have an interesting place in mathematics, and they can do one of 3 things. Sometimes we have to discard the remainder. Sometimes we have to force the answer up the next highest whole number, and sometimes we have to round to the nearest whole number. And it's going to be important that you show students when these different scenarios will arise and within what context so that they can really understand what a remainder does. Take a moment and pause this presentation and read and try activity 8.5 on page 172 of your text. It gives you an opportunity to explore with the topic of factors and how arrays can be used to help students conceptualize what a factor is. It also helps students to really explore the ideas and notions between what a prime number is, a number whose factors are just one in itself, versus a composite number, a number who has factors other than just one in itself. The Illuminations website also has a factorized applet that's available, and you could search for it by accessing Illuminations.
It's really important, as we discussed with addition and subtraction, that you model the key properties of multiplication. With multiplication, it is indeed commutative. Division is not. Order does matter with division. It does not with multiplication. And one way you can visually represent that to students is with an array, as I've shown with Exhibit A on your slide. The associative property for multiplication, you could really illustrate this with a contextualized problem. Let's say you tell your students that you are going to sign them each up for tennis camp. They're going to get, as part of their registration, 6 cans of tennis balls. Each can contains 3 balls, and each ball is $2 a piece. Please figure out the total cost of balls that they will have to pay. Well, you could illustrate to them that they could do the multiplication in any order. They could do the $2 times the 3 balls per can of tennis balls and get that they're paying $6 per can, and then multiply that by the 6 cans to get $36. Or they can use another order. They could say, okay, I have 3 balls in 6 total cans, so I'll multiply those together first. I have 18 total balls, and I know that they cost $2 each. In either case, they're going to see that they indeed get the same product of 36. But you can illustrate it visually in a much more effective way, I think, than just putting out a strand of numbers and showing that you're lifting up parentheses and moving them. The contextualized problem will help it to be more meaningful and help it to cement more in their minds. A couple other key properties that you're going to need to discuss with your students are the zero and identity properties of multiplication and division. You don't just want to state the properties, but you want to present them through contextual problems because it helps the students to better reason with 0 and 1. Here's a couple examples. You could ask the students how many grams of fat are in 7 servings of celery if celery has 0 grams of fat. They then have to think that through, and they realize that 7 times 0 is 0, and that's always going to be the answer regardless of the grams of fat. Another way for them to think of it visually is, where would 0 hops of 5 put you on the number line? Well, they realize that they're not moving at all. And again, visually they're able to see the 0 property. You can also model the 0 property with an array. You could try to have them construct 6 by 0. A great property to illustrate with an array is the identity property. So showing it for maybe 6 times 1 would be an excellent way for them to visualize that property. Concerning the distributive property, for visual learners, you can use arrays just as I've shown on the screen. That might not be many students' preferred way. For instance, I just understand it algebraically, but we have to remember that we are educating students with multiple intelligences, and for many of them they are more visual, so the array does present it in another way, and it still shows you that when you decompose a problem into multiple factors, it still is equal to the overall product, and they can see that presented with the array or area that we have presented in the figure on the slide. One other thing you're going to want to talk about is division by 0. And you don't just want to tell your students, well, that's undefined and impossible, but present it in a way, again, that's put into a context. Like ask them, can you take 12 balls and place them equally into 0 groups? That helps to cement their understanding of the property because they realize they can't take something and put it into nothing. It has to have a place to go, and that's why the division by 0 is undefined. Sometimes students can feel frustrated with context problems simply because they're uncomfortable with not getting an answer right away. And there are some tactics that you're going to want to encourage them to employ so that they can generate patient problem solving within themselves. First, you want to encourage them to focus on the problem in the meaning of the answer instead of on the numbers themselves. So we want them to be thinking about process and what is actually happening in the problem. Second, you want them to focus on the structure and identify what numbers are important and which one are unimportant. You also want them to think about what the answer will tell you. If they're thinking about what the answer describes or relates to, they can then work backwards and determine which inputs or which numbers are the most important in the problem. Third, you do want students to estimate their answer, because estimation is a great way to cross-check if once you get the answer it seems reasonable. And we want students to be able to think of reasonableness often by judging their actual answer with a rough estimate. I would suggest for students that seem to be struggling because a problem contains really difficult numbers, either they're very large or they're fractions or they're decimals, and the students are struggling with the computation, you can encourage them to substitute small whole numbers for all the relevant numbers in that more complicated problem. That helps them analyze context problems that seem to be tripping them up. And another thing they can do, or you can do, is once you've replaced those relevant numbers with smaller whole numbers, you can model the problem with counters. You can write an equation to solve the problem. You can then even solve it, because then the students can see that the process remains the same and they can go back and substitute their more complicated numbers in.